I'm very excited we're going to hear what John he's going to tell us about going back to the basics.
Cool. So, hi, my name is Jan, and I'm old. There's no way around it. And because I'm old, I like to talk about old stuff, and so let's go back in time. Just out of curiosity, and the hands are probably going to be the reverse of what Aurora just asked. How many of you are born after 1985? Yeah, I kind of expected that. I'll come back to 1985, but let's go back 10 years earlier. 1975, this is the Altair 8800. And it is sort of kind of considered to be one of the first home computers, which means that it's something that you can buy as a person, bring home, and then do computing of sorts. And we don't really use the term home computer anymore. You know, that's another term for that would be microcomputer. And my phone that sits here would like to argue with this guy about being a microcomputer. Maybe we should call them nanocomputers. I don't know. But anyway, so the term home computer stems from the fact that it was sort of in distinction to what computers were back at the time, which were mini computers, which were like fridge size. Talk about mini, or like actual computers, which were still, even in 1975, like room size, large rooms full of equipment to run corporate stuff. And the Altair is relevant in one specific way because this here is one way of delivering software, and this particular piece of punch tape actually contains the first version of Microsoft Basic. And Microsoft Basic, written by Bill Gates, Paul Allen, and another guy called Monte Davidoff, who helped with the floating point stuff, is sort of the first product of Microsoft. And they sold it to Altair, and so the Altair came with Microsoft Basic, or you had to, I think you had to buy it actually for several $100s, and you would get this roll of punch tape. A little bit later, throughout the end of the 70s, beginning of the 80s, we saw this wave of home computers that, like we think of, the C64, the BBC Micro later on, the ZX Spectrum for the British people. Yeah, that's when the home computer market really took off, and those were commercial machines. And there's a reason why I like these systems, this first generation of home computers is because they're really simple. And if you are a human being with enough time and enough energy, you can gain a complete understanding of this computer. And with complete, I mean complete in the sense that you understand how the hardware works, how the software works, how all the extra chips work, what timing the instructions have and everything. And I am not that person, but I know people, who have internalized every single aspect of, for example, the Commodore C64. And so coming back to 1985, this was my second computer, the Commodore Amiga. Was launched in 1985. The Atari ST was launched in 1985. Macintosh launched in 1984. The IBM PC launched in 1981, but really just gained traction a couple of years later. And these are all 16-bit machines. The operating systems get more complicated. The hardware gets more complicated. You have all this extra power, but obviously also this extra complexity. And for the Commodore Amiga 500, there are people who know very much about it, but it's kind of the cutoff point where it becomes impossible to fully understand what this system does at all times, as one human being, that is. So my first computer was actually a Commodore C64, and it came with BASIC, and that's what we're going to talk about today. So BASIC stands for Beginner's All-Purpose Symbolic Instruction Code. Rolls right off the tongue, right? So some basic facts. It was created in 1963, at Dartmouth College by John Kameny and Thomas Kurtz. Now, 63 computers looked very, very different, right? It was meant as a compiled language for multi-user systems, so a large system with lots of terminals, and was meant to replace Fortran. We've heard about Fortran yesterday, briefly, in Mats's talk. And Fortran is a very clunky language. It's not easy to write, not easy to read. And they wanted to have something that they can actually give students, also students that are not computer science students, to build simple software. And since BASIC is very simple in its design, it was easy to then port it to smaller systems and write interpreters for that. And Microsoft BASIC is actually one of the first interpreters for home computers, for these small computers that I've been talking about. And most home computers from that era actually use some version of Microsoft BASIC. There were a couple of alternatives, but most of them used Microsoft BASIC. So does the Commodore C64, even though it doesn't say Microsoft anywhere here. That's what license agreements give you. And this is the screen that comes up. We're going to see it in a second on an emulator. That comes up when you start the machine. So the machine is in BASIC. You can start programming BASIC here. There's no in-between. That's what I like about these computers as well. They scream, program me, the moment you turn them on. Quick example for people who have never seen BASIC. So how many in here have actually programmed BASIC at some point? Well, that's a lot of hands, but I expect that to be something like Visual Basic as well, which is very different from what you're seeing on the screen here. There are elements that are similar, but also elements that are very different. So I'm not going to explain what this does. I think, like, if you put your mind to it, you can understand what it does. It's going to be on the slides for a while. So let's talk about the stuff that actually stands out from like a modern perspective. The first one is that BASIC is loud. It's all uppercase. On the C64, there's actually a trick. You can hit one key, and then everything will be shown in lowercase. But it's just the characters on the screen. The actual data is still uppercase. So it helps if you think that this is annoying, but it's really all uppercase. We have very short variable names. I know this is a bad example because we're still using the I for loops. At least some of us do sometimes. I'm guilty in that regard. But they cannot be much longer than that. So on the C64, the only thing you get is 2 letters or 1 letter and a number, and then a suffix for the type, but that's not important. So you run out of variable space really quickly, especially since all variables are global. There's nothing like local state in BASIC, at least not in this version. And there are no functions. Well, there are functions, but they are weird. They are like mathematical functions with 1 argument, and it can only be a mathematical expression, so not functions in the sense that we like to talk about functions today. And also no arguments. So you see the goSub there on line 20, and that's calling a subroutine on line 100, and then the subroutine returns, but there is no data that is like pushed between those. You have to do that in global variables. And then the last thing that's probably bothering you the most is explicit line numbers. And there are a couple of reasons for that. The sort of boring reason is that we use it for addressing, so goSub 100 would be kind of like, how would you write that? There are no labels or anything, no jump marks, so that's the easy part. But the real reason is that when BASIC was actually created, that was at a time when the computer interfaces looked very different from what we have today. And even the C64 doesn't have what we would now consider a proper editor. Everything was line-based, so you can type a line and then hit enter, and it gets entered into memory. We're going to take a look at that later on. But there's nothing, you cannot scroll through your code or anything. And back in the days, your computer interface probably looked like this. So this is a teletype. It has a keyboard and it looks like a typewriter if you're old enough to know what a typewriter is, right? So you type stuff into the computer, it gets sent via a serial line or something, and then if there are any results, it gets printed out on paper. Screens were not really a thing back then. And so well, at least not generally available. And so by using line numbers, we can quickly make changes to our code by just typing the same line number of the line we want to correct, and then type the line again, and we're done. So let's have a quick look at that. So here is Vice. That's a C64 emulator. Let me try to write a quick program. Okay, and this line is now entered into memory. And let's do the obvious. So there's some line editing, but not much. So this is the obvious one. Let's take a look at that so I can print it out again with list, and then I can run it. Woo! That's exciting, especially if you do it in an electronics store in the 80s. It was like, I hacked this system or something like stupid like that. Now, the cool thing about BASIC is that it has immediate mode, and list and run were already two immediate commands. So I can do something like print 2 + 2. And so writing BASIC is a little bit like writing all your Ruby programs in IRB or in Pry. And to me, that feels awesome because there's no disconnect, right? Now, the interesting thing about this emulator is that it comes with a machine monitor, so I can actually take a look at what's happening in the machine. There were similar things for the C64 itself, but here it is very comfortable because I can just run it in a different window and take a look at the internals. And so I happen to know that the BASIC program sits at address 800 or 800 because that's all hex. And so we can take a look at the program, and you can see it there. It looks weird because somehow the print and the goto is missing, but the data is there. You can see the string, and you can see the goto 10, like the line number. So let's have a look at what that actually means in the data. So I've highlighted a couple of numbers here. So the first one is a 0. There's a reason for that. It's kind of dodgy, but every BASIC program starts with a 0. That's just the way it is. And then we have two bytes which are in reverse order. I keep forgetting if it's big endian or little endian. I'm sorry. I wanted to write it down and I keep forgetting it. So it's one form of endianness that is the one that I can't remember. So the address it's pointing to, this is an address it's pointing to, it's the address of the next line of the BASIC program. So in this case, it's 81C, and that is on line 2 behind the 0 there. If you know your data structures, that's a linked list. That's how the BASIC program sits in memory. After that, we have the actual line number, and that's in reverse order as well. So that's 0A for 10. And then we have the 99, and the 99 is the token for the print command. So something has happened with that line and it has been so-called tokenized. And there's a couple of reasons for that. One of them is just memory consumption. The other reason is that we can easily turn that into a jump table, into the routine for the BASIC command. And then it's actually ASCII. So there's a 20, that's 32. If you know your ASCII code, that's a space. And then 22 or 22 is the opening quote. Then we have our string. Then we have a closing quote. First of all, the 21 is the exclamation mark. Then we have the 22 closing quote, and then a 0. That's the end of the line. And then we have the next line, which starts off with the address for the next BASIC line, but there is no next BASIC line, so it just points to a couple of zeros, and then the interpreter knows, okay, here's the end of the program. Which makes me think about the modern development workflow, right? Because we have this, like if you think about it, you're writing your Ruby code in an editor. Like maybe, let's take the worst example, let's take VS Code. Not because I don't like VS Code, but just because it's, it's so much. And so you have probably a textual representation of your Ruby program in there, and probably a couple of dozen other representations, like maybe an AST for the syntax highlighting, and some plugins that need some form of parsed content. And then you write that to disk, So it sits on disk, probably in a couple of versions because you're versioning your files, right? And then the Ruby interpreter loads that into memory. So I'm pretty sure there's a textual representation in memory somewhere, and then that gets parsed. So we have an AST of sorts. I'm not an expert in how the Ruby internals work. I've heard that there are people at the conference who probably know a little bit about that. And then something happens, and then we can execute the code. And on the C64, it's like you enter it, it's in memory, it's executed from there. That's all that happens. Let's find out what's going on. So I spent the last few weeks trying to figure out what the C64 actually does. And how do you do that? So the first source is this. This is a book from 1988. It's called C64 für Insiders, so C64 for Insiders in English. And among other things, it contains a complete disassembled listing of the ROM of the C64, so both the kernel and the basic interpreter, with comments. It's like literally, it's 300 lines of disassembler code, like on the right-hand side there. It's a little bit tedious to read this in a PDF. I think I had the original once, but I'm not sure. I gave it away, if so. And obviously, there's more modern variants. So there was a guy called Lee Davison who did this amazing English version of that. It's very similar, but it's online and with cross-references and everything. So this is a really cool thing. Unfortunately, he passed away a couple of years back, which is a tragic loss for the retro computing community. And then there's the work of Michael Steil, who's a German gentleman as well, who took all of that, and I think I have it open in a tab somewhere. There you go. So this is a website that contains not only the disassembly on the, let's go to an example that actually makes sense, like the disassembly on the left-hand side, but also the original source code from Microsoft that has been leaked at some point, and then various commentary you can switch on and off if you want to, in English, in German, in various variations, and that somehow made it possible to figure out what's actually going on. I'm going to show you as soon as I'm back on my slides. So we're going to take a quick look at a little bit of 6502 assembler. Don't be afraid. If you don't, like, who in here has done some form of assembler in uni or something, or maybe even in a job? Okay. I mean, 6502 assembler is odd, but it is relatively easy because it's a small set of instructions. Don't be afraid, I'm going to explain everything. What we're going to take a look at is a very small piece of code, which is the basic warm start. And that's essentially, if you have entered a basic line, it's going to jump back to the basic warm start, and then everything starts from scratch. So this is the piece of code. This is reformatted from Lee Davison's website. The format is as follows. On the red column is the actual memory addresses. Then you have the bytes that the code is comprised of in memory. And then you have the disassembled instructions, so what these bytes actually mean, and then some comments. So we start off with JSR, which is already like a bad start because we're immediately jumping somewhere else. So jump to subroutine. I just wanted to show it here real quick because it does something interesting. So we're jumping to that memory location, but also we're putting a return address on the stack. So we're putting the current address where we add onto the stack so that we can jump back to that code. So it's a little bit like GoSub and return in BASIC. What does that routine do? We are not going to jump into that because that's long. It waits for the input, so you type away your line, and at some point you're going to press return, and then it's going to, and while it does that, it copies the characters that you enter into a buffer, and then X and Y contain the buffer address. And it jumps back with RTS. What does RTS do? It does the return thing, right? It pops the address from the stack, and then it jumps back to that location. And that is actually used as a trick. obviously the stack is something we can push arbitrary values to, so we can actually push a different address onto the stack, then let someone call RTS, and we can use that as a jump table thing. So that's something to be aware of, because that makes reading the code much more difficult. What's X and Y? So these are registers. If you know your assembler, that's a very typical thing for processes. You can think of them as single variables, like single addresses of memory or places of memory, but they are sitting on the CPU itself. So we have the program counter, which just holds the current address and is incremented before any command is run. Then we have the stack pointer, which points to the current stack. The stack on the 6502 is annoying because it has only 256 bytes, and it doesn't do any boundary checking. So you push one more thing to the stack, and you've ruined everything because you're now at 0 and everything is gone. The accumulator is sort of your main register that you use for calculations and everything and comparisons and stuff like that. X and Y are sort of general purpose registers you can use for loops and stuff like that. And then you have the status register, which is kind of important because it holds a lot of flags that do things like, okay, I have this operation and now the accumulator is 0, for example, then the 0 flag is going to be set. If the value in the accumulator is negative, then the N flag is going to be set and stuff like that. Next two instructions, STX, STY, store the contents of the X and Y registers into a memory address. Now the memory address looks a bit weird because it's just 1 byte, and that is because the the 6502 has an optimization called the 0 page, which means that you can address the first 256 bytes of memory by just using that short form address. They are different opcodes, so the addressing is you have to use a different opcode for those 0 page instructions, but the assembler figures that out on the fly. And the cool thing about this is that you need less memory for the instructions, and also it's faster. Then we actually jump into a routine that sits in the 0 page, but the 0 page is RAM, so something must have copied that routine into memory. That's done by the basic interpreter initialization. And the reason for that is because we can now, with this routine sitting in the 0 page, we can access the 0 page even more efficiently, and that makes it work out. We're jumping to char_get. That's a very important routine that is used a ton. It increments the pointers in 7A, 7B, so the values that we've just written to there, and reads a character from there and sets a couple of flags. We are using TAX to transfer the accumulator, where our current character sits, into the X register. That's not important. What's important is that we used an instruction that actually sets the 0 bits, depending on if the number that we've copied there is 0 or not. Why is that important? Well, we want to figure out if the byte that we just got is 0, because if it's 0, then someone just hit return on an empty line, and we want to jump back to the warm start. So that's exactly what we're doing with this branch if equal. Branch if equal, kind of a weird name for saying branch if the 0 flag is set. But if you do a comparison with a compare instruction, then it's going to set the 0 flag as well. Next, we're doing an immediate load. You can see that by the hash mark. That means that we're not loading from memory address FF, which would be a 0 page address, but we're actually loading an actual value, in this case -1, because FF is -1, into the X register. And then we store that into 3A, and 3A is another memory location in the 0 page that holds the current basic line number. Why do we store -1 there? Because if the user didn't enter a line number, we are in immediate mode, and the -1 signifies immediate mode. Last thing here, almost last thing, that is a little bit complicated. Branch if carry clear is another branching instruction that looks for the carry bit, and the carry bit is something that usually happens in subtractions and stuff like that. You know, carry. You hopefully know what that means in mathematical terms, and in this case, we are not actually, like it's not, like we didn't do anything that would set or clear the carry bit, except that we call charget, and charget uses that to tell you if the character that's in there in the accumulator is actually a digit or not. And so if it is a digit, the carry bit is cleared, and we are jumping off to a different part that I'm not going to show that will take the line, tokenizes it, and then stores it into memory. But we are not going to go there. We assume that we did something like immediately. So we jump to the tokenizer. That's going to do the replacement of the keywords into tokens. And then we just jump to the interpreter. This is a jump instruction, so there's nothing put onto the stack. So there's that difference. So it's a go-to in basic terms instead of a go-sub. And yeah, that's just the interpreter start point. Let's turn that into Ruby. That's really not that much code. So we have a read line. And we parse the line of the first, like, I mean, I shouldn't have used a regular expression here. That's very modern and very, it doesn't make a ton of sense. But if the first character in the line is a digit, then we're going to store that into memory. And if not, we're going to parse it directly and then run it. A couple of other key core concepts in the basic interpreter. The first one is the tokenizer. And it's because it's like we would do it differently in Ruby, but because it's, we only have so many instructions that we can use, what it basically does, it compares the current character against a table of other characters that hold the keywords, and then if it matches, you go one character further, and if it doesn't match, you jump back to jump to the next keyword in the table. And there's a weird way how these keywords are actually put into memory. So this is just pseudocode, and actually it's not even half the truth. There's like lots of special cases that you have to think about. So it's a bit of code. The interpreter itself is like deceptively simple. You look for a token, you look up the routine in the table, you call the routine, and then you start again. It's a little bit more complicated than that, but that's the gist of it. So one thing is missing from here. You may or may not recognize it. There's no handling of arguments right now. And that is because the handling of arguments is like handed down to the routines themselves. So for example, if we have something like a print, right? The question becomes like, okay, this is a mathematical expression, but what shall we actually print in the end, right? And so the print routine just calls a thing called the formula evaluation, form eval, and it uses a separate routine called eval, which will just fetch one value from the expression. And so I kind of thought about like how to best explain what's happening here. And I know this is something that is probably relatively similar in modern interpreters because it is a complex problem. And you have to deal with so many things like precedences, for example. And so I'm going to show you how the C64 does it in hopefully an understandable way. So we're pulling the opening parenthesis, and this is already a case where we now actually recurse into the same routine again because we know that everything that sits within the parentheses is actually going to be another expression. Then we read the digit 2. We're going to turn that into a floating point number because in the basic interpreter, everything is handled as floating point numbers. We're going to put that into a memory location that is called the floating point accumulator. Then we are going to parse the next thing, which is a token, which is the token for the addition. And because things aren't complicated enough, we're going now to store all of that onto a stack together with a number, and that number is the precedence of the operation. And then we're going to pull the next digit. We're going to convert that into a number. And then we are going to parse the next character, and that's a closing parenthesis. And that just means that we need to unroll the stack again because it's the end of the expression. So now we are going to actually call the addition operation, the second number is pulled into the second accumulator, and we have a result. And now we read the next instruction, and guess what? It's put on the stack. And you can see it's a different precedence, right? The other one was 7, 9, and this is 7b. Now we read the 5, turn that into a number, and we read the next token, which is the plus. And now something interesting happens, because we have a precedence that is actually lower than the one that sits on the stack. And that means that we need to unroll the stack first. So that's what's happening. We put the operation aside, we unroll the stack. So that's going to, the result is going to be put into the first accumulator again. That's 20, if my calculations were correct. And now we can put all of that on the stack again. And now we encounter a different thing, which is a function. So that one needs to start with a parenthesis. So that is just syntax checked. Is there a parenthesis? If not, it's a syntax error. And then we encounter something completely different, which is a variable name. We can just look up the variable name. We get a 0. That is lucky because it's easy to calculate. So we are going to calculate the sign. It's going to end up in the accumulator again. And then we check for the closing parenthesis. And now we know that the line is ending because we have a 0. And now we just need to unroll the stack. And we end up with the end result of 20. And that now needs to be turned into a string. I'm not going to show you that. And then we can print it. I have to admit, like reading this in assembler and figuring out what jumped where and how it nearly broke me, but I figured it out in the end. And I got it to work, and it's a fascinating bit of code that can probably be refactored to something very, very simple, because I'm still using a stack, even though like recursive function calling in Ruby works fine. Yeah, that was the hard part. It took me about half a week or so to figure that out. So there's a thing called Ruby Basic somehow. It's roughly 1,000 to 1,500 lines. I haven't counted it recently, of terrible Ruby code. It's gonna sit after the break in the afternoon. It's gonna sit at this address. And yeah, it surprisingly actually works. So I've reconfigured my terminal here, but I can assure you that is a Linux terminal, like a normal shell. It's a Z shell. And I can just run Ruby Basic. And I didn't want to count any memory, so and I can just type my code here, and I can list it, and I can actually run it. Whoa! Ah, yeah. See, and so I just typed the number again, the line again, and I mean, and you have to do it uppercase. So, and I even implemented, and that's probably I should exit here and start it again, because I didn't implement the clear command yet, which I just wanted to show you that. Let's see if that works. Basic sign txt. I just wanted to show you that it also does slightly more complex things. So if I run this, I get a nice sine wave. Cool. So how much time do I have? A couple of minutes. That's good. What did I learn? So Microsoft Basic is a work of art. It sucks in many regards, but it is a work of art to get that working on such small footprint and like with all the tricks they've been using. I can only, like, it's weird, but I can only encourage you to try to understand what's going on there, because it's such a humiliating experience of like figuring out how they did stuff back then, and how ingenious a few of the things, a lot of the things were that they were doing there. Obviously, it's a very different world. I think the most important part is that like everything was constrained back in the day. You didn't have disk space. Like loading from disk was extremely long-winded, if you had a disk, that is, if you didn't have to use paper tape, for example. And nowadays, we live in a world of like almost unimaginable abundance in terms of memory, in terms of disk space, and we sometimes forget that people actually have slow phones in their pockets, and that sometimes we need to optimize for certain things. It's really hard to transfer to Ruby sometimes, I think, because I didn't want to use GoTo. I don't even know if GoTo is still a thing in like modern Ruby. It was when I started with it, but I don't even know if it's still working. So it took me a while. One thing I learned is that global state is good, actually. Especially if you're trying to implement something like this, it's almost impossible to do it without global state. And I learned that the hard way. I tried to prevent it, and it didn't work out. So obviously that's not great for some cases, or for most cases. But in this case, it helped a lot. And the last thing I want to talk about a little bit is complexity, because honestly, like, what are we doing? So if you think about how modern software development looks like, and this is, I try to find a better image, but what I meant to express by that is like all the different abstraction layers that we put on top of each other. Like if you think about like a modern web application built in something like React or any web framework of your choice, and then you have a backend in Ruby maybe, but you have so many layers of things that have to work together to actually display something very simple on the screen. And there's so many CPU cycles lost to that, I think, and so much energy spent, and sometimes to good causes, and sometimes to causes that are maybe a little bit questionable. And it's not like I want to go back. Like, I like this world of abundance. I like that I can just spin up servers and do stuff with them. But I think it's time to become a little bit more aware of where we are, what kind of systems we build, how much is actually abundant and how much is just abundant because there's a lot of, like, to be fair, less cheap money on the market than there used to be. But like, think about our impact on the systems that we build, and also think a little bit about the incentives. Like, why did we build systems like that? I find it kind of fascinating, a report that I recently saw, and I don't want to particularly bash Microsoft for this, but it was such an interesting thing, where they basically abandoned their CO2 saving plans for the next 20 years because they have to build a lot of data centers for AI stuff. And what they answered when they were questioned about this is, well, AI is going to save us all, so it's fine to invest that now. And I don't know about that. I really don't know about that. So I think the incentives are sometimes on like the side of like, let's build more, instead of figuring out like if we can maybe dump down the stack a lot and be more efficient with what we do. And so at least try not to pile on. Some last acknowledgements. I want to thank Michael Steil, he's a German gentleman, so Michael Steil, Lee Davison, and also the Vice team who built these incredible emulators that allow you to experience these computers without actually having to get your soldering iron out, opening up old machines, replacing all the capacitors because otherwise nothing is going to work. And so it was great to just be able to throw this up and play with things. And then I also want to thank my beta testers. I think actually maybe one or two people are here who are hearing this talk for the second time, because I was able to beta test it at RubyUnConf last weekend, and it's definitely gotten, I hope, a much better talk by being able to do that. So with that, I am Jan. I am the co-founder of DebFu. We do automated dependency updates. I'm a freelance web developer, digital artist, sometimes when I find the time to be a digital artist. I'm sort of kind of looking for work, so talk to me. I'm not on Twitter anymore, so you'll find me on the Fediverse, and I am also a moderator on Ruby Social. I'd like to point that out because we're doing some good community work there, I think. And then everything else you will find at halfbyte.me. And with that, thank you very much for listening. Thank you very much for listening.
Yeah.